How's it going, everybody? In this video we are going to take a look at what it takes to form an adjacency with OSPF. And OSPF being actually my personal favorite protocol. I like it actually a lot more than the EIGRP. I think it takes more to understand. That's why I tend to gravitate towards OSPF. And so what we're going to do is we're going to take a look at what is needed to get OSPF neighbor adjacencies to form, what are required, or what things are required, what things are optional, and then we'll get into a little bit about how the database works. Once we form a couple of adjacencies, I'll break it down. And we're going to do a single area implementation in this video. So I'm going to have a peering between router 3 and 5. I'm going to show you a couple different variations of peering, whether it's through we're going to take a look at peering with the network command and with the neighbor command on directly connected links, and then as we go farther along we'll get into more complicated things like multi-area implementation, modifying the network type, and we'll take a deep dive into OSPF, and rightfully so. It's a lot of companies run OSPF, especially in multi-vendor environments. It's very it's widely used, so I think it's needed to be gone into in depth. And like I said, it happens to be my personal favorite protocol. So now, when it comes to forming adjacencies, neighbors must agree on attributes to form adjacency. So not all OSPF neighbors actually form adjacency. So what I mean by that is if you have let's say you have 4 routers, and each one of these routers is connected to a switch, and all the routers are plugged into the switch in the same VLAN, so they all can talk to each other. They're able to ping each other's IP address, and everything's working in that regard. Well, what ends up happening is if you have 3, 4, 5, 6 routers all connected to the same switch or on the same broadcast segment, what you end up getting is only 2 of those routers will actually form full peerings, and the ones that will form full peerings are the designated router and the backup designated router. They will form full peerings with all 4 of the other routers, or however many other routers there are to plug into it. Let's just go with 4 for the time being. So there will be a total of 4 full adjacencies. Or I'm sorry, 2 full adjacencies. You'll have the peerings between the non-DR routers to the DR and the BDR. So it'll be technically 4 adjacencies, 2 to each one. And they will form full adjacencies. Now, you can form an adjacency, you can form a neighbor relationship but not actually form an adjacency. And the difference between the two is when you're dealing with a broadcast or an MBMA environment, you can run into where you run into kind of a hub and spoke environment, and then it won't be full mesh. What this means is the DR other, which means that routers that have not been elected to be the DR or the BDR, so any other DR other is what they're referred to, those guys are going to form two-way adjacency with other DR other routers. So it's only all DR other routers will form full adjacency with the DR and the BDR. They will go to two-way with each other. So DR other to DR other will form two-way. And two-way basically means that you have exchanged hellos with each other, but you haven't gone to exchanging your link state database. Now, what ends up happening is when a DR other router peers with a DR or a BDR, what ends up happening is he exchanges his full link state database with the DR. Then the DR then replicates information out. So the DR other to DR other peering doesn't exchange this database, but the DR other to the BDR and the DR, that there's a link state database exchange there, and then the DR and the BDR then replicate that information down to the other DR other routers. So that's the basic idea to it, and we'll talk about more of this in detail. I'm going to be doing a lot of debugs as we go through, so that'll help send home the details to all this on how it actually works. We'll actually run through the the debugs and talk about how that actually comes into place. A unique attribute is included, which is the local router ID and local interface IP addresses. There must be an active router ID available, or I'm sorry, there should be an interface that is able to be used as the router ID locally to the router. If there is no router ID, you won't be able to turn the OSPF process on, and that requires an up-up interface. Unless you're dealing with there's no way to get around that. You have to have a router ID. And a router ID is going to have the same format as a IP address, but it isn't actually an IP address. It's just a 32-bit address that takes the form of an IP address, and you don't have to have a route to the router ID. The router ID, like I said, you can make it any arbitrary value you want. You can make it all 255s if you so choose to. And what will end up happening is, if you do make the router ID something that would technically not be an IP address you'd be able to place on an interface, those are a little more common to see because of the fact that, or I shouldn't say common, but it'll make a little more sense that that's a router ID because of the fact that it's not applicable for an IP address at the interface level. Now, you don't have you don't have to have a route to the router ID. However, when you're dealing with other things like the advertising router, if you get into a situation where you are trying to get in, especially when you get into external LSAs and stuff like that, and I don't want to get too far ahead out of the gate here, but you'll find that you'll need to have a route to specific identifiers, and you won't have to have routes to other specific identifiers. The router ID is a route that you don't is a string of text that takes the form of an IP address that you don't have to have a route to. The advertising router information you do have to have a route to, and we'll talk about that more when we start getting into the forward address and some of the other things that come into play with that. Some of the common attributes that must match is, in order for two routers to form a peering with each other, they must be in the same area. And the hello and dead interval must match, and the hello interval is how often we talk to each other and how long we wait before declaring the remote neighbor down. So hello interval is how often we say hi to each other. Dead interval is how long do we wait before I say you're down. Interface network address, you must be on the same subnet unless you're dealing with PPP unnumbered link, and I don't recommend you do that. I've never had good luck with that, and I think it's just a lack of support with GNS3. But the interface MTU is going to be needed to match, but that technically doesn't have to be set up correctly. You can actually do an ignore MTU in a lab environment. It's fine, but when you are dealing with a production environment, MTU can actually, if it's a mismatch and you're trying to send more than what the next hop can take, then you could actually break the adjacency and lose your peering. The network type, they must be compatible. Now, if they are not compatible, you'll get to the exchange state, you'll go through, you'll form an adjacency, the link state databases will exchange information with each other, but the problem will be is when you actually get to when you get to run SPF and actually take the best routes from the link state database and install them in the routing table, they won't go in the routing table. And the reason for that is because if you have a mismatching network type, for instance, if you have point-to-point on one end and network on the other, or broadcast on the other one, then one is using a Type 2 LSA, the other one is not. And we'll get into that more in detail later on, but that just gives you an idea of how that would break down. Authentication, there's like 4 or 5. The first one is default, which is null or no, so you don't need authentication by default with OSPF. Then there's clear text, which is type 1. Type 0 is none. Type 1 is clear text. Then you have type 2, which is MD5 or SHA. And then you technically have, when you get into IPv6, you can do IPsec. And it only works with IPv6 with an IPv6 address. So I'll show you guys how this works when we get into the IPv6 section, but it's actually really straightforward for the most part. It's just a matter of you going through and making sure you have you have your updates are encrypted, it takes the authentication, in my opinion, to the next level, because encryption is going to be more, it's going to be much stronger than authentication. And then we have stub flags. Stub flags are things like the stub area, the not so stubby area. So a stub, so area whatever stub, area whatever stub, no summary, is different. So that's a different type of stub than the NSSA or NSSA no summary. So a stub route or a sub router will not receive a type 4 or 5 LSA, which is going to be anything external to the OSPF domain. Where in not so stubby areas, they will not receive a type 5, but they will receive a type 7. Or I should say they won't receive type 4 or 5, but they will receive a type 7 LSA. And we'll talk about that in more detail later. I'm going to deep dive into LSA so you guys understand how that works. Some of the other capabilities that are out there that aren't really talked about too much, but they're still applicable to some level, is the opaque LSAs, which are extensibility, which allows you to do advanced features in MPLS and stuff like that with traffic engineering. So the way that forming adjacencies breaks down at the end of the day is a cost value. So lower bandwidth equals a higher value, and a lower bandwidth equals a lower value. So if you have a high bandwidth, you're going to have a higher value for your cost. So the cost is typically going to be directly related to your. I'm sorry. Whoa. I totally had that backwards. Slower bandwidth is higher value. Lower bandwidth has a higher value. Or it has. I'm sorry. Lower bandwidth. Slower bandwidth, higher value. Higher value. Lower bandwidth, lower value. I had these reversed. Higher bandwidth, lower value. Sorry about that. Because I was like, wait, no, that doesn't make sense. So, for instance, if you have a 10 meg link in OSPF, the the cost is directly related to the interface bandwidth. So, and it automatically relates to 100 megabits per second. So, if you have a 10 meg interface bandwidth configured, that means that the cost is going to be a cost of 10. So, because you take 100 divided by 10 is equal to 10. Once you hit 100 meg, it's going to be a cost of 1 because 100 to 100 is 1. And then anything above that is going to be 1. Now, you can change that with manipulating the to the reference auto-reference cost bandwidth, and that's actually going to allow you to raise the bandwidth up and make a higher functioning. It changes the bandwidth to be higher so that you can set the reference bandwidth to be a cost of 1 is going to be, say, 10 gigabit, and so a 100 meg link would be like a cost of 1,000. So, and then the database. The link state database must be the same on all routers in order for the SPF algorithm to work, and this is per area. So, if you're in any area, all the routers that have a connection to that router or to that area should have identical link state databases. Once you leave that area and you use an area border router to get to the next area, then what's going to end up happening is the area border router is going to have copies of both areas, and he's going to advertise into both areas Type 3 LSAs. A Type 3 LSA is an area border router or a network link state or a summary link state. And we'll get into that more in detail when we actually get into it, but that has to be the databases have to be the same, and we'll talk about that more when we get into the details of how that actually breaks down. So when we get into media dependencies, OSPF behavior changes based on the media type. So Ethernet versus frame relay versus PPP. So Ethernet and frame relay both default to a broadcast type network configuration. So Ethernet is broadcast, frame relay uses NBMA. The NBMA and broadcast are the exact same type of network protocol, or a network media type. They both form, they have Type 2 LSA exchange, which means that there's a DR BDR election process there. Now a PPP defaults to point-to-point, and it does not use a Type 2 LSA. So we'll talk about that more in detail coming up as we go in. But different medias uses different network types to control. So how updates are sent, who forms adjacency, how next hop is calculated, that type of stuff. So with broadcast, you have on a broadcast network, it's the default on multi-access broadcast medias like Ethernet. Sends hellos to the multicast to 224.0.0.5 to all SPF routers. That's everybody. And 224.0.0.6 to all DR BDR routers. And performs designated router and backup designated router election. So we'll talk about that more in detail as we come up here. But what I'm going to do is I'm going to bring up our diagram. In our diagram, we're going to be running OSPF on this link right here, which is the only link we have in Area 0. And we're going to get that running here and talk about how that goes into play. So on router 5, what we're going to do is I'm going to type in do show IP interface brief. And we have a connection going between router 5 and 3 on fast 1/0. So what I'm going to do is I'm going to type in router OSPF 1. And let me actually take this step back and go router OSPF and 1. This number here is just the process ID. This is locally significant. So now what you could do when you're dealing with the process ID, you can have more than one process ID running on the router at a time, but anytime you want routes from one process ID to go to another, you have to redistribute them. So we'll talk about that more later, but we can definitely demonstrate that coming up. So, but like I said, the process ID is unique to the router. It's arbitrary what you use, but if you have more than one process ID on the same router, you need to redistribute them if you want the processes to exchange. So think of them as two different instances of OSPF. Now, if you have router 5 here is running process 5, and then router 3 is running process 3, they're going to form adjacencies, no problem, because like I said, it's locally significant. So we'll type in network of 172.16.35.0 0.0.0.255 area 0. Now, what this is telling us is this octet, this guy here, so it's 172.16.35. By typing this network command in, I'm actually telling the router, go out and look for any interface that's configured with this IP address, and I want you to match on the first 3 octets. That's what these zeros mean. Zeros mean that this must match, this 0 means this must match, and this 0 here means that this must match. 255 means I don't care. That's why they have the 0 here. And I'm going to hit the hit the enter key here. That's going to start sending the OSPF hellos out. Now what I'm going to do is on router 3, and this is just a basic implementation, and you can ignore all these OSPF packets that you see and stuff like that. I was actually playing with some configuration earlier, and that's why I have it set up the way that I do. So now what I'm going to do is I'm going to type in do show IP interface brief, and I have the connection going to router 5. So I'm going to type in router OSPF 3 network of 172.16.35.0 0.0.0.255 area 0. Now when I hit enter, it's going to take up to 40 seconds for this to appear. Do show IP OSPF interface brief. What this means is, let me actually bring this up a little bit and explain this more in detail. Interface fast 1/1. What this is telling us is that we are the wait timer. That's why it says we're in waiting right here. What we're actually waiting to do is determine who is going to become the DR on the link. That's what this wait timer is for. Now, there is ways to disable this and to tweak it, but I'm not going to get into that in this series. And there we have it. We have the neighbor adjacency is up. I'm going to hit the up arrow, and now we are the DR. Now you might say, well, how did that happen? Why did you become the DR? Well, the reason why I became the DR is because of the fact that the IP address that I have here. So I'm going to type in do show IP interface brief here, and my highest address here is 100.113. 100.113 is higher than 10.255.33. So my router ID, router 3 became the designated router on the link because he had the highest router ID. When you're dealing with your DR BDR election, by default, any Ethernet interface is going to have a DR priority of 1. Same thing on router 5. If we type in do show IP OSPF interface fast 1/0, I have a priority of 1. I'm the DR. My router ID is 10.255.55. So that tells me that because of the fact that my router ID is lower than router 3's router ID, that means that router 5 is going to become the BDR, the backup designated router. Now, any other routers that I would join to area 0 would be DR other. We'll take a look at that when we come over here to area 123 over here with 1, 2, and 4 when we do this, where I don't know who I'm going to have become the DR, and a router can be both a DR other and a DR depending on what area it's in. So, for instance, here router 3 is the DR for this link. He could be the BDR for this link, where router 2 could be the DR for this link right here between 1/0 and 1/1, but be the DR other on this link in area 123. So it just depends on how you how it all plays out. But at the end of the day, knowing what the differences is pretty straightforward. I have a broadcast network type by default because it detects Ethernet, and the reason it detects Ethernet, if I was to type in do show interface fast 1/0, I am using the encapsulation of ARPA. My bandwidth is 100 kilobits per second. I have a delay of 100 seconds, which actually doesn't have anything to do with it here because of the fact of what type of protocol it is. We are OSPF, and we go based off of the interface bandwidth, and we are living it good. This is just a way for the good folks over at GNS3 to have a little bit of fun with us. So that's how you break down what's going on here. Now, since we've done this, nothing else is actually working. And you might ask, well, what do you mean nothing else is working? Well, we shouldn't be advertising any routes, and the reason for that is because when you have directly connected networks like this guy right here, there's no reason for it to advertise a route. The only time you advertise a route is when you're bringing something external, or when you're using the protocol to route to another interface. Because we're peering on the same connected interface, we don't have to worry about it. So, because it's a connected interface, we're good to go. What we're going to do now is on router 5, I'm going to go to interface loopback 0, and I'm going to type in the interface level command now. I've used the network command, which is used in the global process, but let's say, for instance, that you are at the interface level already. You can use the interface level command to place a interface into OSPF, and the command is IP OSPF and the process ID of 5 and the area it's going to be in, and then we're going to put it in area 0. Okay, now it goes into area 0. We're going to do the exact same thing on router 3. I'm going to type in interface loopback 0. I'm going to type in IP OSPF 3 area 0. Now what I do here now is I'm going to, and you can ignore this piece right here. Do show IP route OSPF. I've learned one route from router 2 or router 5. I've learned a 10.255.55. So now if I was to do a do trace to 10.255.5.5 and source it off of my loopback 0, because I advertised router 3's loopback into OSPF, I'm able to reach it. He knows how to get there. So that's one of the things that you'll see as you go along on how this breaks down. Now another thing I'm going to do is I'm going to type in show IP OSPF, and there's quite a few options here. I'm going to type in interface, and I'm going to type in brief, and this is going to let me know, this gives me a quick look at what I've got going on here. So we have loopback 0 is advertised into process 3 by process ID 3 in area 0. This is the network mask that I'm advertising. The cost is 1. It's in loopback state. The reason it's in loopback state is because of the fact that we use interface loopback 0. OSPF automatically will detect that and give it the loopback state. we have 0 neighbors and we have no full or connections. Now on fast1/1, we're process of 3, area 0. This is the subnet range that I'm peering with, cost of 1, and we are the DR, and we have 1 neighbor that's fully connected. That's what that means. So if we come back over here, we type in do show IP OSPF, and we type in neighbor, we're going to have 1 peer. We have 10.255.55, which is the neighbor ID. This is router 5's address that we're using to peer with router that's advertising himself. Priority of 1, because that's the interface priority. We have router 5 is where he is fully peered with us, but he's a BDR. That's how much time he's left on his dead interval, and it should go no longer than 30 seconds, and then it should automatically reset to 40 seconds and count down because it's a 10-second hello timer. I'm also going to type in traffic and interface fast 1/0 1/1. And this is just giving me an idea of what type of traffic is going back and forth, which really isn't a whole lot. Now I'm going to take a look at the show IP OSPF database and hit enter. Well, right now we don't have a whole lot going on because we have a very small network. We have 2 routers with a single peering between each other and 2 routes being advertised. Now, the advertising router, this is the router ID. This is who's advertising routes to me is 10.255.55, and I'm advertising a route of 100.113. So this is my peering in area 0 to router 5. The link ID is 255.55, which is the loopback, as well as, and then this is the other link ID, which is me advertising my link in. This router LSA means the directly connected links on that particular router, and the network link state, this is the type 2 LSA, which is going to be your DR. Now I'm going to type in router LSA, and I'm going to type in 10.255.55. I'm going to right click and hit enter. What you're going to get here is you're going to get the details to router 5. Now what I'm doing here is I've got what router 5 is advertising to us. The advertising router, that is him. That is router 5. He's letting us know that he sent us 2 links, or information about 2 links, and these are the 2 LSAs that we received. We received the stub network, which is his loopback with a /32 mask, and we received the transit network, which is how we're getting to router 5 on this particular subnet. This is the advertising router's IP address that we use to peer with him. Now, if we were to look at this guy, type in network or network and this guy. That's us. We can't do that. Let me go to router 5 and type in show IP OSPF database, or show IP OSPF database. And so now we're going to be able to do this. So now we'll be able to do database for the network and grab this guy. Actually, no, link ID. It's this guy. This is what I should be able to. There we go. So this is what router, this network right here, this link ID. This is what router 3 is advertising to us. So we have. This is the advertising router. This is the link that he's advertising to us. And what he's telling us right here is from router 5, we have a designated router. The routing bit is set so we can reach this particular address, which is where we're actually not advertising that. We're advertising the loopback in. And if I was to take a step back here and go type in the router for that, I'm going to get information as to what he's got. He's advertising me 2 links. This is his router ID. This is the advertising router, which is router 3. We have the stub network, which is router 3's loopback with a /32 mask. Then we have the transit network, as you can see right here. And then we have the IP address for learning on the peering. Now that's all pretty straightforward for the most part, but at the end of the day, when we start getting into more complicated designs, this is going to quickly grow and become relatively complicated to understand and break down. And I'm bringing this in piece by piece so that it's relatively straightforward to see. So what we're going to do in this video, I'm pretty much done with it. I want to just do a basic breakdown of how everything works. And what we're going to do in the next video is we're going to then bridge ourselves into a full multi-area implementation where we have connections to 3, 2, 1, and these 4 routers are going to be fully paired with each other. And we're going to have connections to both directions, and we're going to take a look at how we would route traffic both ways and get to where we need to go. Now, with that being said, once we start doing that, the OSPF database is going to start to grow very, very rapidly. And the problem with that is it's going to become more and more difficult for you, if you're not familiar with the OSPF database, to be able to try to translate what it's telling you. So I can look at this and go, okay, well, I know what's going on. All I have to do is look at a couple different LSAs, and I can tell you what's where and why it's there, and what's being advertised. So that's the general idea of how you can go along and figure out stuff. But at the end of the day, it's important to be able to interpret what you're seeing, and this is exactly how OSPF is able to build the graph of the tree, like I mentioned in the overview video. Build the graph of the tree, and then from there we were able to take a look at this in more detail and say, okay, well, we've learned how the router LSA works, which is every router in an area is going to advertise all of its directly connected links to the other router. That's what a router LSA is. In the situation that we have here, we are using the network type broadcast on the connections between 3 and 5. Therefore, a BDR election is applicable, which did run. Router 3 was elected because he had the higher loopback address. He had the higher router ID. He won, and so now router 3 is advertising us 2 links. The link to get to him plus the stub network that he's got configured to him. The more and more I add to router 3, if I was to advertise the loopback in here, you'd see this advertised. So let's go to router 3 real quick, and from global config, interface loopback 100, IP OSPF 3 area 0. Now what I'm going to do is I'm going to go over to router 5 and hit the up arrow. I'm going to have a third LSA in here. Third LSA is going to be the stub network of the loopback 100, and you see how quickly that came across. Now, if you're paying attention here, let's take a look at this. This is what I was just looking at a moment ago. Notice the LSA age is 348. That's 348 seconds old. So now if we come down here to this one, this one's 5 seconds old, which means what? It was a brand new LSA, so that the LSA age automatically restarts. The LSA age will automatically be flooded in a broadcast network every 30 minutes or every 1800 seconds. So we have the loopback 0 of router 3, loopback 100 of router 3, both of their masks, and then we have the transit network to get to router 3 and the IP address we're using to perform on him. If we were to go to router 5 and type in interface loopback 100, and don't worry about what you're seeing there. I'm not sure why that's handling it. Actually, I moved this entire setup from one computer over to another, so that's probably why this is happening, but I'm not too worried about it. So loopback 100, we're going to type an IP address of 100 or 10.100.5.5 or 15/24. Okay, and IP OSPF 5 area 0. Oh, area, not era. Area 0. Now I'm going to go to router 3, and I'm going to jump out of here. I'm going to type in show IP OSPF database, and I'm going to look at the link state for this guy. So I'm going to hit the database for the router and right click and paste this guy in, and I'm going to get my transit links. So here we have it. Now what I'm going to do, notice how on 5 I can, did it again. On 5 I advertised the loopback with a /24 mask. But on 3, he's only at a /32. Well, to fix that, we can type in IP OSPF network type as point to point. Okay, now we go back to 3, and on 3, we're going to hit the up arrow. And notice the LSA age is 14. We're going to hit enter. The LSA age is 9. And now look what happened. So 10.100.5.0/24. Can I still reach it? Ping 10.100.5.15. I certainly can. That's a good sign. And everything's working. So that's how LSA updates. And notice how, if we also come back up here, when my LSA age changed, look at my sequence number. 8 and a lot of zeros and a 4. Now I changed it to LSA 9, age is 9 of 9 seconds, and then a sequence number of 5. And that's how it's able to determine whether or not it's good. The checksum also changed. C7B to bed 6. So as you can see, things are starting to change. The number of links is starting to increase, and everything looks good. So I'm happy with what we have going on here. Everything looks pretty good. From here on out, we're gonna in the next video, we're gonna take a look at getting into a multi-area implementation, which I think everybody will get a kick out of that. There's a question: when am I going to do OSPF authentication? I'm planning on doing authentication coming up once I break down how the different network types work, get everything fully converged in OSPF, and then from there what I'll do is I'll get into authentication, and we'll talk about clear text, area-based, link-based, and then doing clear text and MD5 and all other good stuff, because there's a little bit more to it than just XYZ. It does take a little bit of understanding of how this stuff works. So that's the basic breakdown of the link state database. Again, fair warning, it's going to get more complicated as we go along. But as long as you, I'm going to do my very, very best to go slow and methodical and explain how things work and how the when your link state database starts to grow and you're trying to work on your LSA recursion. So how do you move from one LSA to another to finally get to your end destination? I'll break that down, and hopefully it'll make a lot of sense when we get there. But I can only do what I can do. So I hope this has been informative for you, and I'd like to thank you for viewing.